Hi, I would like to explain the most representative model PointNet. It is no exaggeration to say that almost all 3D models refer to PointNet. Existing methods used a mesh, volumetric information, projected view, and vectorization, and so on. But this method had limitation as follows, so PointNet occurred to overcome this limitation. PointNet used the raw point cloud data, and it uses the deep learning method called multilayer perceptron. The goal of PointNet is directly to directly consume point clouds which will respect the permutation invariance of points in the input. Also, it provides a unified architecture for applications like classification, part segmentation, and semantic segmentation. As you can see here, the input data size is n by d dimension. Here, d means the number of point cloud data, and d means the feature of the point cloud data. And it is generally used XYZ coordinate, but the additional feature can be color and normal vector and so on. So in the task of classification, the output can be the k-scores for all the candidate classes. For the segmentation task, the output has to be n by m scores for each of the n points and each of the m semantic subcategories. In the point cloud segmentation task, it has the common issues as follows. Invariant permutations, invariance to rigid motion, interaction among points. First of all, invariant permutations. Unlike pixel arrays in images or voxel arrays in volumetric grids, point cloud is a set of points without specific order. So, in the case of point cloud with d dimension and n order data, then the model needs to be invariant to n factorial permutations. The result of the model also have to be same about all n factorial permutations. Second, invariance to rigid motion. The learned representation of point set should be invariant to certain transformations, like translation, rotation, and so on. So the the result of classification and segmentation um, do not have to be depend on the transformation of the data. Lastly, interaction among points. Points are not isolated, and neighboring points form a meaningful subset. This is this is the architecture of PointNet. It is composed of several layers like multilayer perceptron, max pooling layer, and transform network here. So this is the figure from the source code, GitHub source code of PointNet. MLP64 and 64 means the output layer size is 64, and then there is one another multilayer perceptron with the output layer with the 64 output layer here. So when we see this code, the for the input data, 1 by 3 1 by 3 size filter is applied for the input data. And then for the multilayer perceptron here, 1 by 1 size filter is applied. And this 64 and 64 means the size of upper layer is 64. And then here, after the feature transform, there are 64, 128, 1024 output layers from the multi-layer perceptron. And then after max pooling here, it, it is processed by multi-layer perceptron and fully connected um, it is called fully connected layer because the size of the size of the layer is 512 and 256. And K means the alpha scores in the classification task. So in the architecture of PointNet, there are three key components. First one is symmetry function for unordered input. Effectively, the network learns a set of optimization functions and criteria that select interesting or informative points of the point cloud and encode the reason for their selection. So, as a symmetry function here, this architecture used the max pooling layer, and when each input passes the multi-layer perceptron, we can obtain local feature here. And after aggregation of these local features, we can process the max pooling. And then after multi-layer perceptron, we can obtain the global feature here. The author compared various kinds of method for the invariance of permutation like LSTM and MRP with unsorted input, MRP with sorted input, and so on. Next one is next key component is local and global information aggregation. For the classification task, the output from this section forms a vector like this. And with this global feature, we can process SVM or multilayer perceptron for classification. However, point segmentation requires a combination of local and global knowledge, so we can concatenate the feature from the middle section of the classification network, and also we can concatenate this with global feature here. So by this process, we can extract new per point features based on the combined point features. Next is joint alignment network. In this architecture, two transformation networks are used here and here. So by the first transformation network, we can obtain 3 by 3 dimensioned transformation matrix. And here we can obtain 64 by 64 dimensional transformation matrix. So by using data-dependent spatial transformation network, we can canonicalize the data before the PointNet process them. This paragraph is from the appendix of PointNet. So it describes the architecture of TNet, and it is composed of three multi-layer perceptron, and the output layer size is 64, 100, 128, 1024. And then there is a max pooling layer and two fully connected layers with output size 512 and 256. The concept of TNet is came from the spatial transformer network, and the reference is here. So spatial transformer allows a spatial manipulation of data within the network. So after we obtain the data from this network, we can calculate a sampling grid that determines the location of the sampling point in the input feature map according to this data. And then we can apply the sampling grid to the input feature map to create a converted output feature map. So here the author um, used the loss function, the specific loss function. They constrain the feature transformer matrix to be close to orthogonal matrix because they thought um, when they has when they have the higher dimensional matrix, then it would be more difficult to optimize the transformation matrix. So orthogonal matrix means uh, it is the matrix with the which the column vectors and row vectors are has the size 1. So we can constrain the size of the matrix, size of the transformation matrix. This paper showed 3 different experiments, which are classification, for segmentation, and segmentation task. For the classification task, they used ModelNet 40 and it has 40 man-made object categories. It showed the state-of-the-art performance like this. And also, in the case of part segmentation and segmentation, they also showed good performance, good MIOU here. For the part segmentation, they used ShapeNet with 16 categories, and for semantic segmentation, they used S3DIS dataset. Also, they did additional experiment. They showed when they used both 3 by 3 transformation matrix and 64 by 64 transformation matrix, and then the outcome was best here. And then also they tested the outlier ratio. When they applied the outlier ratio, they still had the good performance. This is the end of the PointNet, and I'd like to introduce some concept of PointNet++. Compared with the original CNN, PointNet has some limitation. A CNN takes the data defined on regular grids as the input and is able to progressively capture features at increasingly larger scales among a multi-resolution hierarchy. So in CNN, the deeper the layer gets, the wider the receptive field gets. So it can have the larger receptive fields. However, PointNet does not capture local structure induced by the metric because it uses the full features immediately. So to deal with this problem, PointNet++ first partitions the set of points into overlapping local regions by distance metric of underlying space. So here in this figure, we can see the points are sampled and grouped, and then each group is processed by PointNet. These 3 steps they are called set abstraction. In here, N means the number of point cloud data, and C means the three coordinate XYZ coordinate of the data, and D means the additional features like color, normal vectors, and so on. So after sampling and grouping, we can see the dimension of the data is changed. So this N means subsampled points, and this K means number of points in the neighborhood of centroid point. So given input points, the FPS farthest point sampling is used to sample the point, and then Bar Curry finds all points that are within a radius to the curry point. Here we can see a specific process which is called skipped link concatenation. In this step, we can do concatenation of two vectors, and one vector is obtained by summarizing the features at each subregion from the lower level using the set abstraction level. And the other vector is the feature that is obtained by directly processing all row points in the local region using a single PointNet. So by doing this, we can solve non-uniformity problem of data.